Greetings, and I would like to welcome you to this B-WaterSmart training activity on the so-called UWOT tool, the Urban Water Optioneering tool. And today we will explore in a session that spans approximately 2 hours what the model can do for the design and simulation of smart water systems at different spatial scales. And we will also see what UWOT can do for specifically for B-WaterSmart. Yes, my name is Dimitrios Bouziotas from KWR, and together with my colleague Stavroula Manouri from NTUA, we will be providing your content on this training activity for UWOT. So following our presentations, we would like, of course, we would be happy to receive any questions in the discussion section, as Archodi has indicated in our agenda. And our emails are also found in this slide if you have any questions after this course and after perhaps trying UWOT yourselves. Now a bit of more information on the layout of our presentations today. You've already seen the general agenda by Archodia and know the general layout. As you know, we start with two presentations. The first one is a general presentation on UWOT that consists of 4 parts. Firstly, an introduction on the context and role of UWOT, simply put what UWOT does. Then a brief mention on the methodology, which is the way UWOT works, but we will reveal more details in the next demonstration, the video with the hands-on demonstration by Stavroula. Thirdly, there is a mention on the experience and knowledge we generated from using UWOT in past projects. And lastly, we close with the conclusions and the applicability of UWOT for the smart water systems of B-WaterSmart. Following this, we will have a step-by-step demonstration on how to build and run a system from scratch using UWOT, including choosing the components, handling inputs, simulating and viewing results. This will be through the video of my colleague Stavroula. Now let's start with a bit of context relevant to B-WaterSmart, where we focus on smart water systems and management. As you know, these systems have unique attributes. For instance, they employ an array of different technologies that can be applied at different scales. For instance, demand reduction measures such as water smart devices are employed typically at the household level, but other decentralized technologies such as rainwater harvesting or greywater recycling can be employed at the neighborhood scale as well. Moreover, there are technologies such as water banking or blue-green systems which are applicable regionally. Moreover, these smart systems have a high complexity and multiple flows in the urban water cycle, which are affected. There are, for instance, cascading and interacting effects in drinking water, stormwater, and evidently wastewater by introducing these smart water measures. And at the same time, smart also means digital, with new technologies being introduced, such as innovative pilots and smart sensors. And lastly, another aspect of designing smart systems is that we need to include the socio-environmental factors as well, as these factors drive the demands essentially and affect the future water availability. It is evident, therefore, that we are in need of smart tools for smart systems. In short, we need the tools that are generic, meaning that they are able to represent cases at multiple spatial scales, starting from the household scale and up. We need tools that are holistic, models that provide a bird's eye perspective on the water systems, so the whole picture of how a water system behaves and responds in terms of water. This allows to study smart systems where multiple water flows interact, such as drinking water, rainfall runoff, groundwater, and wastewater, and grasp the causation and cascading effects of different technologies. We need tools that are modular, so we need models that are able to include new sources, represent new promising technologies, and tools that can be also used supportively to explore how small-scale pilots can be upscaled. And finally, we need a scenario-based approach in our modeling, where we also simulate what if possible futures in the systems, and we can change social or environmental factors and immediately see their effects and stress test our technologies. So as a tool that is fit for water smart systems, we introduced UWOT. an urban water cycle model to fit these needs for smart systems. UWOT is a modular simulation engine built for smart water, and I will explain all of these terms in a minute. By modular, I mean that UWOT offers an interface to build systems using bottom-up component logic from the demand points to supply. Now, as a simulation engine, we mean that the model offers daily and hourly simulation capabilities. So it has a quick engine built in C and Python, able to simulate scenarios that span years to decades. And finally, it's a model built for smart systems, as it addresses the points we have mentioned before. UWOT is thus able to model a range of different technologies at different scales as components, including rainwater harvesting, grey water recycling, blue-green areas, and smart water appliances. It is also able to include data from multiple sources, including sensors. And finally, it provides functionalities for scenario-based modeling, either by changing technologies or by changing the driving factors of demand and the availability for water, for instance, based on social or climate data. UWOT is already a tool with medium to high technology readiness, TRL level. It comes with its own interface in Windows and comes as part of WaterShare, which is a network of tools addressing water issues in various thematic areas. So UWOT is thus accessible to WaterShare partners, but it is also accessible to the B-WaterSmart projects and the partners as well, with a limited license for personal use. So please contact us if you would like to try it out further yourselves, besides this first display at the workshop. And we already have interest from some of the partners to try the model out themselves, so we are quite happy about this. Now, focusing a bit on the methodology, we said that UWOT is a bottom-up tool, able to model technologies as components that generate demand or provide supply. In fact, UWOT is able to model different categories of components, 5 of them. Firstly, as the basis of modeling, it's able to model household appliances, so conventional and water-smart household appliances. Secondly, it's also able to model district network components, such as pipe networks, with an aggregate lumped approach, but also wastewater networks. Thirdly, it's able to model signal connectors, which allow different components to multiply their demands and interact with each other. Another category is hydro system or supply components. These are the different water sources available to cover demands. And finally, there are other components, smart components such as blue-green areas, which are covered in the broad named Nexus category. So UWOT models always from the demand side and up. This is a tap-to-source model starting at the small scale, so the household devices that you see here in your right screen. And it then proceeds to match these water demands with available sources in the right side of the model, but also logs the generated wastewater and regional runoff. So as we will see in the hands-on demonstration, a typical water system with UWOT, a topology, so to say, that is a term that we will use often, is built in 4 stages. Firstly, we add the household appliances and mix them together under different groups that represent the different households. You can see each household in this example in the picture with different colors. Each color represents different households. So we group these components together to represent a household with different demands, different people, and so on. Secondly, we include decentralized local supply measures such as rainwater harvesting and grey water recycling components. So we match some of these household and neighborhood demands with the local supply. We also simulate runoff from roofs with special components. So you can see these additions here. And finally, at the right side, we include the supply points. So we log using special components, water quantities such as the stored water in tanks, the covered demands, the required energy, evaporation from areas, and so on. Once we build the topology and complete the simulation, we can view all the time series results as graphs or export them to Excel for further analysis. Of course, UWOT is not only about simulation, but comes with a complete methodology to develop and compare scenarios derived from different backgrounds, for instance, based on climate, technology, and social changes. try different designs or fine-tune a particular scenario, for instance, by changing the parameters of specific components or technologies, such as the capacity of a treatment unit, the size of a tank, and so on. And finally, we can extract the model output, aggregate the outcome, and present it in a more concentrated, aggregated layout, for instance, through a dashboard to key stakeholders. So we can use UWOT as a decision support tool. Let's now progress to the section on past outcomes. UWOT has over a decade of development across different research projects, being actively developed since 2012, since its first conceptualization. It has been thus applied successfully in a range of European cases at different spatial scales. And now we are going to see some recent examples in the slides that follow. In the beginning of 2019, UWOT was applied successfully as an ex-ante evaluation model for a circular neighborhood in Limburg. This was a joint consultancy project with VML, and the neighborhood was named Superlocal. This was a redesigned neighborhood with the aim to create a smart neighborhood that followed the principles of slow, less, and local, meaning slow, a neighborhood that has a slower runoff response, retaining rainwater locally through a combination of rainwater harvesting and a sustainable urban drainage system. Less, meaning less water use per household with the use of water-aware devices. And local, meaning water being recycled and treated locally through a rainwater harvesting and greywater recycling system. UWOT was then used to conceptualize and model two different neighborhood scenarios, two different neighborhood redesigns for Superlocal. The first one with households featuring distinct decentralized systems. So one rainwater harvesting and one greywater recycling systems that were separate from each other. The second one was a scenario featuring a combined recycling system where rainwater harvesting and greywater recycling led to one treatment unit for this mixed light grey water that was then used to cover some of the household demands. This is the scenario you see in your screen. UWOT was then used to provide quantitative output for both scenarios and compare them with the standard neighborhood. We were then able to see the effect of the Superlocal smart water neighborhood on, for instance, reducing water demands for different household types, reducing the demand that is asked from the centralized systems, the drinking water systems, as well as projecting changes in the wastewater that flows into the network, which also depends on the type of scenario. And thirdly, we could view the effects on runoff reduction for the different neighborhoods as well. And the results were presented in a feature paper on designing circular water neighborhoods using a modeling-based framework. Following this application, UWOT was applied in the NextGen project, focusing on water in the circular economy. There were two applications, one local and one regional in NextGen. The local application that you see here was in Athens, Greece, where UWOT was employed to model a sewer mining unit in an urban green area. The sewer mining unit is a decentralized wastewater treatment technology that reuses water locally for non-potable uses. Now, the role of UWOT in that case was to support decisions for different pilot layouts, so different modular units, different tank sizes, and calculate the BOD concentration based on the variable wastewater influx that is the source point of this sewer mining unit. This resulted in a number of works describing the impact of this particular smart sewer mining technology, where upscaling and financial dimensions were also explored. Besides the local application in Athens, UWOT was employed in a much larger regional case in the Netherlands for NextGen, with a total area of 410 square kilometers. This was done to demonstrate circular water strategies in the Delfland province. That is the use of different decentralized measures at a provincial scale now to achieve circularity. We considered both urban areas as well as horticulture irrigated areas in this province. So in this more complicated example, we started by drawing the system as it is now, the baseline, so to say, the present case. We then designed different circular water strategies, discussed them with the stakeholders who evaluated them, and finally proceeded with the four most popular different strategies to make the province circular. These strategies have varying complexity and focus on different domains. For instance, green that you see here focuses on rainwater use, while water bank, the blue one that you see on the left, focuses on circular neighborhoods and sustainable horticulture in the area. We then model these 5 different cases using UWOT, 5 being the baseline as well as the 4 different circular strategies, and use UWOT concurrently to estimate how resilient the water system is against the uncertain future. This was done across different water cycle domains, including, for instance, drinking water security in the first row that you see in the graph, but also security against the horticulture demands, the wastewater propagation, and the future runoff. So through this process, we have shown quantitatively that circular water strategies lead to more resilient systems across multiple domains of the urban water cycle and secure the province against future changes in population, climate, horticulture demands, etc. So resilience in this sense is shown using these envelopes of reliability that you see in the graphs. To interpret them, you just have to remember that the lower the line becomes over time and the wider it is in the future, the more uncertain and deteriorating the system becomes. So in this sense, the circular strategy of WOT Bank, which is shown here, leads to a much more secure future in terms of drinking water demand availability compared to the present day case, which is shown in black. So following these applications, it would be nice to mention here what UWOT can do for the applications of B-WaterSmart. This is ongoing work, so we cannot present all the results as the models are underway, but we can mention what has been done so far and how we are progressing. Now, UWOT is projected to be used for 3 small regional applications in B-WaterSmart, 2 of them in Flanders, Belgium, where it is used to support pilots in Wouwen and Mechelen, as well as an application in East Frisia, Germany. Now for Wouwen, UWOT is used to explore alternative supply strategies for a drinking water supply system under stress. In this supply system that you see in this picture, a raw water storage basin is currently using inlet water from River Iser, but is facing intake issues due to worsening salinity levels that are too high in recent years. So to counteract this, technologies such as wastewater reuse, but also different treatment policies will be modeled, and their effect on mitigating the risk against an uncertain future for this particular intake system will be demonstrated. We will also stress test these interventions using what-if scenarios on climate change, for instance, a combination of different salinity and the dryness of the river. In the second application of Flanders, which is in Mechelen, UWOT will be used to support an upscale pilot that is being built in the area, combining urban rainwater harvesting with a retention basin that uses water for subsurface irrigation. There are different possibilities for upscaling the systems that will be tested, such as the basin volume, but also the sub-irrigated area. If there is interest from the stakeholders, we could also try to stress test the systems against drier future. So we could see, for instance, the impact on influx, but also the impact on the crops. So the challenge here for UWOT is to include the subsurface irrigation dynamics, because the model does not include such a component presently. So we will extend and explore the model capabilities and generate knowledge on conceptualizing subsurface irrigation in such a setting. Finally, for the application for East Frisia at the county level, we include the whole application looking at the whole picture of the system there, where we will identify and model key supply and demand points and match their connections so that the system can be simulated. The modeling process for East Frisia is ongoing, and now we are setting up the geodatabase needed for UWOT input with relevant data being processed. Following this, we will confirm the demand and source points with the stakeholders and brainstorm the scenarios of changes in the water management. So at this point, I would like to conclude with our general presentation on UWOT capabilities, and I would like to mark the following take-home messages. Firstly, UWOT is a component-based water cycle model, able to simulate water demands in different domains, for instance, drinking water, wastewater, and runoff. It can be used to provide a whole system view, simulate responses, and explore the what-if scenarios. So by definition, UWOT is able for many cases of smart water systems at multiple scales, for instance, household, neighborhood, and region. And UWOT has been tested against multiple cases and developed in a diversity of projects. Now for B-WaterSmart, UWOT is projected to have 3 regional applications and simulate specific water-smart technologies, 2 for different areas within Flanders, 1 with a drinking water supply and 1 with urban rainwater harvesting, and of course 1 for East Frisia. So at this point, I would like to thank you for your attention. You can also find all the references that have been used here if you are interested in reading more about what the model can do. However, I think it's more interesting in this workshop to see this through a hands-on demonstration that will follow shortly based on a video of my colleague Stavroula. This will be a pre-recorded session where we set up a topology in UWOT and check out basic components. And this is all from me. I would like to thank you for your time and attention.